Today in this session, we'll talk about different types of memory management technique and few problems on it. We'll not see paging today, we'll see it in the next session. And we'll see one of the topics which we have left in from the previous session, which is deadlock. Now, before we proceed with this different memory management technique, let me summarize what we had covered in the previous session. We saw that memory is very important resource of the computer, and it has to be utilized efficiently and effectively. In order to do that, we have different types of partitioning techniques, with different types of techniques. Yesterday we have seen that very simple called simple paging or single partition technique. Single partition technique. The advantage of single partition technique is it is very easy to implement. And it is cheap, it's not costly. But we have a lot of drawbacks with this approach. The drawback with this single partition technique is only one process can reside, thereby limiting the multi-programming. It means it doesn't supports multi-programming. Now, because of this, we have the concept comes how to make it is how to divide this memory into multiple partitions. Thereby, we call it as multiple partition memory management techniques. Multiple partitioning memory management technique. So, in multiple partitioning memory management technique, we have different techniques for creating multiple partition. Okay, one is we will fix number of partitions, and will also fix the size of partition, and we call it as multiple partition with fixed number of multiple partitioning technique with fixed number of partitions. With fixed size. Here we saw what is the advantage of this technique. The advantage of this technique is it supports multi-programming, and because multiple processes are allowed in memory, CPU utilization is effective and efficient. CPU plus IO devices are utilized efficiently and effectively. Okay. But the disadvantage of this process is, if a process, suppose the size of the partition is fixed to 8 kilobytes, as we have seen yesterday. If the size of the process is greater than the size of the partition, if size of the process is greater than the size of partition, then we have problem. Okay. And it also supports suffers from internal fragmentation plus external fragmentation. Of course, this fixed number of this also supports So we are talking about disadvantage of this. So now in order to overcome these drawbacks, okay, there is another technique, that because of this, if the size of the process sometimes possible that it's greater than the size of the partition, but still it is possible to execute a process, but so far we didn't talk about virtual memory. Okay. We didn't talk about virtual memory. So we talk virtual memory, paging, segmentation in next session. So here we are just talking without virtual memory. We are only talking on physical memory. So in order to overcome the drawbacks with this fixed number of partitions, where the size of the partition is also fixed, there is another technique called multiple partitions with variable number of with variable sized of partitions. Okay. Multiple partitions, but size of each partition is variable. We call it as MVT. Multi-programming with variable number of partitions, and we call this MFT. Multi-programming with fixed number of partitions. Okay. Now, let us see what is this multi-programming with fixed number, variable number of partitions. Here, what is fixed? Number of partitions here also fixed, and size is also fixed, but size of each partition is not same, or size of each partition with every partition is not same. But whereas in MFT, size of each partition is same as size of every partition. Example is, as I have told you, that if I have 64 kilobytes of memory, then equal number of partitions, and 8 number of partitions with equal sizes have been done. But whereas in multi-programming with variable number of partitions, here we have 64 kilobytes of memory, but suppose 8 kilobytes is for operating system. Now it is possible that you can have 8, or you can have 16, you can have 24, you can have 6, you can have 10, for example. You can have any of these combinations. But here the number of partitions with this size of the partitions, how many partitions we got? 1, 2, 3, 4, 5, 6, for example, and here we have got 8. Okay. So here the number of partitions are also fixed and size is also fixed, but the size of each partition is different from other partition. Now the advantage of this approach is it is able to allow a process whose size is greater than 8 kilobytes. Here it is not possible to execute that process. But the drawback of this approach is, here we are reducing the degree of multi-programming. Here the degree of multi-programming was 8, because there are total number of 8 partitions, and here the degree of multi-programming is only 6. Here we are here the degree of multi-programming has been reduced. We will see few examples on this, and understand how this what are the different algorithms in MVT works. Here we don't need any algorithm here. Another difference is we don't need. The difference between this MFT and MVT is, here the size of each partition is same to every partition, but here it is not same. First, okay, and second is the size. Here it is possible that if the size of every partition, okay, if it is same, then the degree of multi-programming will be more, but here chances are there that the degree of multi-programming is less. Okay. But it is not of course every time possible. Sometimes it is possible in MVT that the degree of multi-programming will be more, and in MFT is small. Okay. It depends upon the size of partitions. And here we don't need any algorithm. Why we don't need any algorithm? Because size of every partition is same. Which partition you want to make, you want to load any process. If you want to load any process into any partition, okay, then you are allowed, because every partition having same size. But here it matters, because there are chances that suppose there is one process whose size is 24 kilobytes, and only 24 kilobytes of partition is available here. But suppose if there is another process who takes only 2 kilobytes, what happens if I have taken this process which is of 2 kilobytes and made it to load into this 24 kilobits partition, even though it is allowed, it is able to execute, because internal fragmentation as a result of this loading will be 24 minus 2, which is equivalent to 22, but the new process cannot execute it. But suppose if I would have taken a smart decision here, if 2 kilobytes will be loaded where in this partition, for example, which is of 6 kilobytes, okay, then this 24 can be loaded into this memory. So here we have to write algorithms. We need to have different algorithms for taking decision as to which process to load into which part of memory. So there are different types of algorithms which comes here. Okay, one is called first fit algorithm, and another is called next fit algorithm, and worst fit and best fit. First fit algorithm, the basic principle or the strategy in which the partition will be allocated for a process is this. It will look from the beginning of these partitions in such a way that if the size of the process is lesser than the size of the partition, if this condition is met, okay, then that partition will be reserved for that process. Okay. So it starts from the beginning, and it will look for all those partitions which are sufficient enough or big enough to accommodate that process. Okay. But what do you mean by next fit? In next fit, suppose the last allocated block is here. In worst fit, will start looking from the beginning, but next fit will start searching from all the partitions from the point where it has allocated last. Okay. So it also works as first fit, but the difference is their starting point. The starting point for next fit is from the point where last block has been allocated, but for first fit, it starts from the beginning of the partition. Okay. Now in worst fit, the how this algorithm works is it will scan all the partitions and finds which after allocating a process, okay, which will leave after loading this process into the partition, okay, which partition will leave a big a greater number of internal fragmentation. Okay, if the internal fragmentation is more after allocating a process in a partition, then it is called a worst fit. And in best fit, after allocating a process into a memory, it should result in less internal fragmentation. Okay. Now this is what the fundamental strategy on which this algorithm works. We will take an example and see with respect to this algorithm how this memory will be allocated, and find the internal fragmentation and external fragmentation and total fragmentation in case of MVT, not in MFT. MFT we did it yesterday. Today we will do it with MVT. Then after that we will talk on dynamic memory partitioning technique. Okay. Then we have paging, but paging will not discuss. We'll discuss on deadlocks. So let's take an example. Assume that we are using OS MVT, variable partition technique. MVT is variable partition, and we have batch processes arriving in order. with the following request. With the following request for storage. The request is 20 kilo, 30 kilo, 10 kilobytes, 100 kilobytes, 60 kilobytes. Assume that we have 4 holes in memory. Assume that we have 4 holes in memory of size, size is also given 50, 30, 200, 50 kilo, 30K, 200K, 16K. $30K. Where would each of the first fit and worst fit algorithm place the processes? Where would each of the first fit and worst fit algorithms place the process? Okay. So now let's solve this. Assume that we are using operating system with variable partition, and we have batch processes arriving in order with the following request for storage. Job 1 is of size, assume that this is job 1 whose size is 20 kilobytes, job 2 30 kilobytes, job 3 10 kilobytes, job 4 100, and job 5, and assume that we have 4 holes in memory of size 50, 30 and 260. So here we'll not take this 30, assume that we'll have this first 4 holes. Okay. So where would each of the first fit and worst fit algorithms place the processes? So let us assume that we have a memory. Okay. Or we'll think like that otherwise. Okay. 50 kilobytes, first 50 kilobytes, you assume that it is used by the operating system. Okay. And remaining 30 to 100 kilobytes, 16 and 30 kilobytes are 4 holes which are available in memory, for example. Okay. So here I have 30 kilobytes, and next I have 200 kilobytes partition, then I have 16, okay, then I have 16 kilobytes, then I have 30 kilobytes. Assume that we are at the beginning of this block. Now using first fit algorithm, okay. Now first request, suppose job 1 is in the queue, job 2 is in the queue, job 3 is in the queue, job 4 is in the queue. When job 1 arrives, okay, now we will see first fit algorithm. In first fit algorithm, okay, I'll name it as partition 1, and I'll name it as partition 2, and I'll name it as partition 3, and I'll name it as partition 4. Okay. Using first fit algorithm, okay, when 20 kilobytes of process comes, then here it will check this condition: is this 20 kilobytes is less than or equal to the size of partition? Yes, it is true. The 20 kilobytes is less than or equal to the size of partition. When it meets, then partition P1 will be allocated for job 1. For job 1, partition P1 will be allocated, but as a result of this, there will be an internal fragmentation. The internal fragmentation would be, the size of the process is 20 kilobytes, but the size of the partition is 30. So 10 kilobytes is of internal fragmentation. So now after allocating it, again, the pointer will be at starting. The last allocated block here is P1. Okay, the last allocated block here is P1. Now when job J2 comes, okay, now the size of job J2 is 30 kilobytes. Now here what happens, it will check. Next, first partition, it is already occupied by job 1. Okay, now when another process comes, okay, when job 2 comes, it will check again this condition, is 200 kilobytes is the size of the process, which is 30 kilobytes less than or equal to 200 kilobytes. Yes, it is true. Then partition P2 will be allocated for it. So as a result of which, the internal fragmentation is, the size of the process is 30 kilobytes, okay, 30 kilobytes, and the size of the partition is 200 kilobytes. So 200 kilo minus 30, it gives you 170 kilobytes of internal fragmentation. So it is considerably very huge, or it's a big memory, internal fragmentation. Now when job J3 arrives, what happens? The size of job 3 is 10 kilobytes. Okay, if the size of job 3 is 10 kilobytes, then it will check, it is filled, it is also filled. Then partition P3 will be allocated. When partition P3 is allocated, then internal fragmentation will be 16 minus 10, which is the size of this job, which leaves in 6 kilobytes. Okay, the next job 4 comes. Okay, when job 4 comes, again it checks. What does it checks? It checks that process P1 is filled, process this is also filled, and job 3, partition P3 is also filled with job 3. Now it has chance to put job J4 in partition P4, but the size of partition P4 is, now here the condition, the size of partition which is the size of this process, which is 100 kilobytes, okay, is it less than or equal to the size of partition, which is 30 kilobytes? No, this condition is not fails, it gets failed. When it gets failed, then this partition will not be allocated for job J4. Now job J4 has to wait till any one of these jobs gets completed. Okay, now thereby it results in an external fragmentation of 30 kilobytes. Okay, and similarly job J5 also cannot be accommodated, because the available space is only 30 kilobytes and the size of the process is 60 kilobytes. So using first fit algorithm, I could able to accommodate only 3 processes in memory, and here the degree of multiprogramming is only 3. Now we'll look with another algorithm and see whether changing when we change the algorithm, is it affecting on degree of multiprogramming or not. So this is how. So total internal fragmentation. So total fragmentation is internal fragmentation plus external fragmentation. Here we have internal fragmentation of 10 plus 170 and plus 6, plus external fragmentation is 30 kilobytes. Okay, so which is equivalent to 186 plus 30, which gives us 216 96. Okay, 216 kilobytes. Now it is when we see job J4 and J5 is not allowed, the total amount of memory they need is 160 kilobytes, but here we have 260 kilobytes of memory which is available. Okay, it means that for this particular request, first fit doesn't gives good performance. Here the utilization of memory is not good. Of course, because we are then the CPU utilization is not good, because the degree of multiprogramming is limited to 3 here for this request. Let us see another algorithm and see how this jobs will be allocated in memory. We'll go for worst fit algorithm. Okay, in worst fit algorithm, it tries to get the maximum internal fragmentation. Okay, in worst fit, when 20 kilobytes is job comes, now it will see what is the internal fragmentation for partition P1. If it has been allocated, then the internal fragmentation IF is how much? So 30 minus 20, which is 10. Okay, but if the internal fragmentation, what is the internal fragmentation for partition P2? Okay, now which is 200 minus 20, which is equivalent to 180. Okay, now of course all other values will be lesser than this value. So partition P2 will be selected for job J1. So job J1 will be loaded, and when job J1 is loaded in partition P2, then internal fragmentation is 180 kilobytes KB. Okay, then another job comes which is J2, and the size of this job is 30 kilobytes. Now it will check 30 and 30, total internal fragmentation is 0, but it doesn't allocate it. It will go and look it here, and it will look it here. Okay, so now here it is not possible to accommodate. It doesn't possible accommodate. So whenever we have a tie, then it depends on first come first serve basis. So job J3 will be, job J2 will be allocated to this partition. When P1 is allocated to partition 1, when job 1 is allocated to partition 1, then total internal fragmentation will be 0, which is 30 minus 30. Then another job which is J3 comes. When J3 comes, the size of this job is 10 kilobytes. It cannot be accommodated. Internal fragmentation will be 6, and internal fragmentation will be 20. So partition P4 will be selected. So when partition P4 is selected, now the internal fragmentation will be 30 minus size of the job, which is 10, okay, gives 20 kilobytes. So job J3 will be accommodated here. Now J4, J5 again they are left. They are unable to accommodate. Okay, so this algorithm also doesn't gives you a good degree of multi-programming, but we observe that the partitions in which the process the jobs J1, J2, J3 are sitting, they are different. Okay, so in first fit J1 was sitting here, but in worst fit J1 is sitting here. Okay, now we'll extend this question for another algorithms called next fit and also best fit. Okay, we'll find what is next fit and best fit in this algorithm. Okay, and what is the degree of multi-programming, we'll see. So here total internal fragmentation. Total internal fragmentation, which is 180 plus 20, which leaves in 200 kilobytes, and which is total internal fragmentation, and total external fragmentation is here 16. Job is not used, 16 kilobyte is not used, so 16 doesn't use. So total fragmentation is 200 plus 16 is equal to 216, which is equivalent to same as first fit algorithm. The thing is, the process has been allocated in the same partitions, but different jobs are sitting in that partitions. That is the difference we saw here. Okay, now let's see what is next fit. In order to run the algorithm next fit, we should know what is the last allocated block. If we assume that the last allocated, initially the last allocated block is nothing. Okay, it will be starting from beginning. Okay, now let's start. Okay, so next fit also works same as first fit, but the process is it will start not from the beginning, but it will start looking for partitions from the point where it has allocated the previous block. So when job J1 comes, so condition is satisfied, job 1 will sit here. So in partition P1, when job sits, then the internal fragmentation will be 30 minus 20, which is 10 kilobytes. When job J2 comes, when job J2 comes, what happens here? J2 again will be allocated here, okay, because the condition is satisfied. So 200 minus 30 gives 170 kilobytes. Now here this will be the last allocated block, but now this will be the last allocated block. Okay. Now when process P3 comes, okay, the size of this is 10 kilobytes. So again it doesn't scans from the beginning, but it starts from scanning here itself. Okay, and it starts scanning from here itself. Now assume that, okay, I am just doing some change. We assume that when process P3, when job, we are talking as job. Okay, no, it's partition actually. Yeah, you're right. Partition P2, P3 partitions. Okay, when job J3 comes, and assume that we are assuming that there is no job sitting in partition P1, and the last allocated block is this. No? Then here we can differentiate between first fit and next fit. First fit and next fit. Now using first fit, if this job J3 comes 10 kilobytes and assume that this is empty. Okay, assume that this is empty. If this is empty, the last allocated block. Now first fit will start scanning from the beginning, irrespective of what is the last allocated block. It goes to up and scans and sees that there is empty, and it allocates partition P1. But so partition P1 will be allocated job J3. But whereas using next fit, the last allocated block was 200. Now what happens? It doesn't scans from the beginning, but it starts scanning from here. So it will check and allocates, partition P3 for job J3. So that is the difference between these two algorithms. Both functionality is same, but the starting point is different, because of which job 3 is sitting in first fit, in partition P1, but in next fit job 3 is sitting in partition P3. Okay. So here of course job 3, now the pointer will be pointing here now. Okay. So then again comes job J4, again also it is not possible to accommodate. Now when you see here first fit and next fit algorithms, this is actually next fit. Those both of us gives us the same output here, because the starting point for both of them was same here. Okay, but when I have taken a situation and assumption that if it is empty, then it gives us different scenario. Now we'll see best fit. Now in best fit, always it ensures that that partition will be allocated after loading a process or job into the partition. It should leave less number of internal fragmentation. Now keeping that in mind, let's see what happens. When first job J1 comes, okay, it is of 20 kilobytes. If 20 is allocated here, then internal fragmentation will be 10. Here it will be more. Here it cannot be accommodated, The choice is either it can sit in process P in partition P1 or in partition P4. Okay, so we resolve it on FCFS. Okay, what partition comes first, we'll allocate it. So assume that job 1 is sitting here. Okay, when job 1 is sitting here, then internal fragmentation is 30 minus 20 plus. When job J2 comes, again it is size of this job is 30 kilobytes. It will not be accommodated here, because here it cannot be accommodated because it is not possible. It cannot accommodate because the internal fragmentation will be more, but here the internal fragmentation is less, so that's why job J2 will sit here and it leaves the internal fragmentation of 0. Okay. Then next, when job J3 comes, okay, it will not be accommodated here because it leaves a lot of internal fragmentation, but it will be accommodated here. So J3 can be accommodated here. When J3 is accommodated here, so then internal fragmentation is 16 minus 10. Then comes a job J5. Now the size of J5 is 100 kilobytes. Then J5 will be allocated because there is no other choice to scan for. Okay. So now here the degree of multiprogramming has been increased. Earlier in the best fit proves to be best here in this case, because 4 number of processes have been loaded here according to this algorithm. The degree of multiprogramming has been increased. Now let us see what is the internal fragmentation. So internal fragmentation is 10 plus 6, which is only 16, but in earlier cases we have got 216, and external fragmentation, in this case it is 0, so total fragmentation is only 16 kilobytes. So for this inputs, it has been proved that the best fit algorithm is good here. But because we don't have any partition left, okay, we cannot accommodate it. Suppose that after some time, if job J1 has got completed, still it is not possible using best fit for this process to allocate this job. Okay. Now assume that after some time, again, if job J5 has been completed, now it is possible for J5 to sit here. It is possible for J5 to sit here. Now in this case, suppose if J4 is sitting here, okay, and J5 cannot be accommodated here, in that situation external fragmentation would be 30, okay, and but it cannot be accommodated here. When suppose if it has been vacated, then job J5 can sit here. Okay. So it depends upon how these jobs gets completed and which partition is available. Among all those partitions, a smart decision will be taken depending upon these algorithms. Okay. Now there is third memory partition technique, which is called dynamic memory management or dynamic partitioning technique. This is very good technique actually. Let us see how this technique works. We saw single partition technique, multiple memory management partition techniques. Here we saw MFT, and MVT, and dynamic memory partitioning. Dynamic memory. Now, what is the advantage of this scheme is, here the size of the partition is not fixed, or neither the size of the partition is fixed nor the number of partitions are fixed. Okay, neither size of the partition is fixed Thank you, sir. Okay, here neither the size of the partition is fixed nor the number of partitions are fixed. Then how does it calculate the size of the partition? Everything, all of this will be calculated dynamically. And the size of the partition and the number of partitions are actually dependent on size of the processes or jobs. Here we have a good assumption that entire memory is treated as a big hole, single big hole, So it's a big chunk of memory. It's big, memory is available. Whenever any process want to execute, okay, how much amount of memory it needs will be allocated from this big hole and will be given to that process. That process takes that memory, executes it, and again return backs. When it return backs, again the size of the hole increases. Now there are a few problems with these techniques as well, and we'll see what are those now, and how does this dynamic memory partitioning technique works. We have one good example on this. Let's write this. Consider a system with 16 kilobytes of memory. The sequence of processes loaded in and leaving the memory are given in the following table. Process P1, 7 kilobytes is loaded. Process P2, 4 kilobytes loaded. Process P1 terminated and returned memory terminated. Whenever it has been terminated, memory will be returned. And memory is returned. Then process P3, 3 kilobytes loaded. Then process P4, 6 kilobyte loaded. Assume that when a process is loaded to a selected hole, it always starts from the smallest address. Starts from the smallest address. For example, if P1 is loaded, then it will be loaded at address 0 to 8 minus 1, which is 7. Since entire memory is one whole, I will take this. Since entire memory is one whole. Now this question is very good. Actually, it gives good understanding of this dynamic memory partition as well. So since the entire memory is one whole, give the memory map showing allocated portion and free portion. Allocated portion and free portion after the end of the sequence. After the end of the sequence. Okay, And if a process cannot be loaded, indicate that which process is not be loaded. Okay. So we have to indicate which process cannot be loaded, one thing, and also we have to tell what is the internal and external fragmentation, and external fragmentation. Okay. And in which case of the algorithms this gives you internal and external fragmentations. Okay. So in which algorithms? Now there is one commonality between MVT and dynamic partition technique, that is the same algorithms can be used here. Right? In the beginning, the things goes very smoothly, but when the sequence of these processes loaded into the memory and few processes gets terminated, then the result of the memory will be entire memory will be having big holes because of few processes loaded and terminated. The memory will be left fragmented. Okay, you'll have different holes at different point of time with different sizes. Okay. So now we'll see how this problem will be solved. Okay. Now we have to show what is the status with first fit, next fit, worst fit, best fit. We take this, okay, and we'll see using buddy system with paging. Assume that size of page is, let's assume it to be 2 kilobytes. Okay. So in next session we'll solve this.